Hi everyone, I'm Ashwin Krishnan presenting performance model and profile level design of a high-performance session-based recommendation engine. This paper is co-authored with Manoj, Nupur, and Sana. Now, starting with a quick introduction to recommendation model. Recommendation models are systems that tries to target the right product to the right audience or user. For example, when you visit a site like Amazon, you see a lot of products being highlighted onto your screen based on your previous interaction with the website. This is essentially a job of a recommendation system. Now, there are various types of recommendation models in the market. One such type is a session-based recommendation model. Here, the session-based recommendation model tries to predict the next item or set of top K items to the user that the user is most likely to click or view next from an anonymous session. Here, the user profile is not available. So the model has to analyze a session that has series of item clicks, and based on the analysis, the model tries to predict the next item or set of items that the user is most likely to view or click next. Now, going with the high-level architecture of an SBR model, the input to the system is a session which has series of item clicks that goes to a GNN layer that captures complex transitions between the items in that session. Then it goes to a position embedding layer that incorporates sequential information of item transitions, followed by an attention layer that incorporates global and recent preferences of the user and provides us a session embedding, which is a representation of an item that the user is most likely to click or view. Here, an embedding is essentially an n-dimensional representation of any item in the system. The output of the SBR is top K items or set or an item that the user is most likely to click or view next. Here, our objective is to provide an architecture comprising of CPU, GPU, and FPGA for high-speed inference of an SBR model. Then now we went with the implementation on the CPU with 52 cores with hyperthreading. We implemented the nicer model that was developed by our TCS team that has an MRR at 20 of 18.72 and recall at 20 of 53.39 on Diginetica dataset. We found that for a real-time inference with batch of one, the overall latency was around 2.36 milliseconds with a throughput of 423 inferences per second. It increased with increase in batch size. For example, at batch of 2048, the throughput increased up to 7600 inferences per second. Now, here the inference has to be done in real time, but during peak hours, hundreds and thousands of users could arrive concurrently. Hence, we need to check whether the throughput could be increased using an accelerator or not. So we went with an obvious choice, that is GPU, because there are various libraries like PyTorch and TensorFlow that supports GPU, and what all we have to do is to type in couple of sentences, and the entire model would be deployed onto a GPU. It's pretty simple for us to deploy using these libraries. And here we found that at lower batch, the performance was a bit lower for the GPU. For example, for a real-time inference, it was just 182 inferences per second. And we found that even with increase in batch size, there was a bottleneck due to graph creation and position embedding layer. Now, the graph creation layer has operations like array concatenation operation, transpose operation, and random memory accesses. Here, all these arrays and lists were treated as PyTorch tensors and being deployed onto a GPU. What we found was the majority of the time was consumed within the CPU activities like various CUDA API calls, including CUDA memcopy operations. So there were a couple of solutions. One is to either go with a fine tuning on GPU using CUDA or go with a different accelerators. Now, FPGA are reconfigurable hardware that has thousands of DSPs and LUTs and even thousands of block RAMs that has great potential to extract higher level of pipelining or greater depth of pipelining. Also, the recent FPGAs have HBM memories incorporated with it. And the thing with FPGAs are that individual banks of HBM can be addressed independently. So suppose we spread the item embeddings across multiple banks, different random embeddings can be accessed simultaneously, giving us a very high throughput. So overall, we see that there's a huge potential to accelerate neural networks embedding fetch operations and graph creations using an FPGA. But on the downside, there's a lot of effort in designing and testing. Uh, Furthermore, there is a huge possibility that once you develop the entire system on the FPGA, you found that the performance is not optimal, which will be a big setback. So we felt there is a need to come up with a modeling technique to estimate the latency or performance of the different layers of an SBR on an FPGA. So we came up with a modeling approach. Here in this example, we could see that the equation implements the product of A into the product of matrix A and B, followed by a bias addition, and we apply a sigmoid operation on that on the product and the bias addition. Here, the innermost loop of the matrix multiplication is fully unrolled. That means there are 8 parallel multipliers followed by an adder tree to add the 8 products, 8 numbers. And all the dependent operations like bias and sigmoid are pipelined within the innermost loop. Furthermore, the parameters like A and B are stored in block RAM with 8 partitions. Here, the partitions are required so that we access 8 elements simultaneously. Now, the estimated latency can be given by the equation iteration latency plus initiation interval into number of inputs minus 1. Here, the initiation interval is kept as 1 for while modeling, which means that an input can be fed after every clock cycle. And the iteration latency is essentially the sum of latency of individual operations, which we found at the earlier stage during while synthesizing individual operations like floating point multiplication, division, addition, and so on. And here you could see the overall iteration latency is a sum of parallel multipliers followed by an adder with 3 stages, then an adder and a sigmoid operation, giving us a total estimated iteration latency of 32 clock cycles. The total number of inputs to this pipeline path is number of rows in A multiplied with number of columns in B. That gives us 20. And the overall estimated latency comes to around 51 clock cycles for this example equation. Now, summarizing this model strategy, the first and foremost step is to record number of clock cycles and resource utilization for each of these floating point operations like multiplication, division, addition, and so on. And the innermost loop of any matrix multiplication is fully unrolled. And all the dependent operations like bias addition, sigmoid, tanh, and others that we even saw in the previous example are pipelined within the innermost loop. And output of each layer is again stored in a block RAM with right amount of partitions. Another important point to remember is that we need to keep the overall resource utilization under 70% of the total available resource. This is necessary to avoid routing congestion that may limit our operating frequency, that further deteriorating the performance. And if there's an overutilization, one simple way is to reuse the resource within the individual layer. Although this will reduce the performance, but there is definitely a trade-off between the resource and the performance. Following this strategy, we estimated the performance of individual layers of an SBR on an FPGA, and we found that the scoring layer, which is a part of the session-based recommendation model, is the bottleneck on the FPGA. Now, analyzing the various results on CPU and GPU and on FPGA, we see that different layers perform differently on different kinds of hardware. Furthermore, different hardware like CPU and GPU also depends on batch size, which again depends on the incoming workload. So taking the example of batch of 2048, we see that the graph creation and position embedding layer being implemented on FPGA rest on GPU gives us the maximum throughput, assuming there is only one instance of each layer. But on the downside, the disadvantage is there are many hops present in the best case scenario. Whereas if we go to option 2, there is only a single hop, but again, we need a network with both FPGA and GPU in the same network. And going with option 3 and 4, it provides a lower throughput, but only one accelerator, namely either FPGA or GPU is required. So there is a slight trade-off between performance and even cost. Going ahead, we experimentally evaluated the option 3, that is, implementing the scoring block, that is a bottleneck for FPGA, on CPU and rest of the blocks on the FPGA. And we found that when we synthesize the different layers, our modeling results closely matched with the synthesized results in terms of latency and throughput. And all these this communication between the CPU and FPGA was established using OpenCL library, and we used the software Xilinx Whitis 2019 for our experimental results, for experimental evaluations. Going ahead, we saw that for real-time inference, for every kernel launch, there was an overhead latency in the CUDA kernel launch function that limits the overall throughput. But even then, we found that for real-time inference, the FPGA CPU architecture gives us almost 6.1 speed up compared to baseline CPU, 14.2x speed up compared to baseline GPU, and 6.1x speed up compared to baseline CPU GPU implementation, where CG implementation is essentially implementing graph creation layer on CPU, rest of the layers on GPU. Now, if we are to implement a batch inference, that is accumulating all the sessions together and sending them as a batch to the FPGA using the command clnq migrate mem objects, we were able to hide these overhead latency and achieve the maximum throughput that we estimated in the earlier case. Now, going with a deep dive into modeling approach of a couple of layers. For example, here we are taking the example, the modeling of the GNN layer of the NICER, which is essentially is GGNN, that is gated graph neural networks. Here, if you see, all the model parameters are stored in the block RAM with right number of partitions, where model parameters are weights and biases of the model, which we obtained during the training phase. And we obtained the the number of clock cycles and number of resources that would be required to do the floating point operations like addition, subtractor, and multiplier. Here, when we synthesized that 200 megahertz, we found that it's 4 clock cycles for addition, subtraction, and multiplication, whereas tan H and sigmoid takes around 12 clock cycles. And furthermore, you could see the dependent operations like bias, addition, and multiplication with A is implemented in a single pipeline loop, and the independent equations, that is 1 and 2, consume separate resources so that both of them execute in parallel. Here again, total number of inputs is k into d, that essentially is number of rows of item embeddings and into number of columns of model parameters h1 or h2, giving us a total number of inputs to be k into d. Initiation interval, again, since it's a modeling, we are taking it as 1. And the iteration latency, again, is the sum of the latency of individual operations. Here, for parallel multipliers, it's 4. For an adder tree with log base 2d stages, it's 4 into log base 2d clock cycles, followed by an adder, multiplier, and vector addition, each consuming 4 clock cycles, giving us a total iteration latency of 44 clock cycles. Now, we add 50 clock cycles as safe margin to incorporate various control logic and load and store operation that comes during the implementation stage. And for d equals to 10 and k, that is a maximum session length, equals to 10, the estimated latency that we find is around 1094 clock cycles. Now, these set of equations are again a part of GNN only, which essentially is GRU in this case. Here we see that all the intermediate stages like reset gate, input gate are stored on again on chip memories like block RAM or registers. Here, one important thing to notice is, suppose we are to implement the independent equations like 4 and 5 separately, like we did in the previous slide. The total number of resources would be a pair of parallel multipliers, adder trees, and an adder. The entire set would be replicated twice, and the resource consumption would be around 1200 DSPs, which would suppose we add up all the resources, would go beyond 70% of total resource available for us. So what we do is, while modeling, we reutilize this set of resource for all 3 parts, all 3 equations, namely 4, 5, and 6. Here, the only difference will be the number of inputs will increase. For example, if we have to parallelly implement all these equations, the number of inputs will be k into d. But since the resources shared, the overall inputs will equal to be 3 into k into d, kd being the number of inputs for each of these paths. Now, overall iteration latency would be equal to the latency of the common path plus iteration latency of path 2, path 3, and path 1. That comes to around 100 clock cycles. Again, if we add 50 clock cycles as safe margin, with the dimensionality d equals to 100 and k equals to 10, we'll get an estimated latency of 3150 clock cycles. Summarizing everything, we developed a modeling technique to estimate the performance of different layers of an SBR on an FPGA. And using this profile-based and modeling-based approach, we found that the heterogeneous kind of an architecture is most suitable for the session-based recommendation inference. And furthermore, we experimentally evaluated the FPGA CPU-based hybrid architecture and achieved a high throughput and low latency. And we found that it's much more better than in baseline CPU, GPU, or CPU, GPU kind of an architecture. Hope you found this session interesting, and thank you for listening.